Okay, so our project is, our idea was we want to fill in missing samples from an audio clip. So, and we got our information from neural indicating, which is the picture on the top. Basically, you get a picture and then you like remove a square from the middle and then you train a model to predict what's in that square. So you just kind of fill it in. And we want to do that idea but apply it to audio. So like if we have like an audio sample and there's some chunk cut off from the middle, we want to be able to like interpolate it and just fill it in to end up with whatever's on the right. So that's the idea, and it can be applied to like if your inputted audio has like noise, or if it gets just cut off, or if it gets like truncated or clipped, then you can just remove it and then we can try to interpolate it back. So that's like the application. Okay, so what we've done so far involved a lot of data collection and processing. So we've collected around 100 gigabytes of open source audio files from arXiv and MedleyDB. And we have processed the data to create features and labels in our data loader object. So what we've done is we trimmed all the samples the same length. We centered the samples. We've dropped the middle samples. So we dropped the samples that we wanted to predict. And we also applied a Fourier transform. So this gives us frequency domain data that we can also train off of. So our data loader object, currently we can either use pure time series or frequency domain data, or we can use a mix of both to train off of.
So our network architecture is a convolutional neural net based off of the diagram below. This diagram is from another research paper for audio super resolution, and we're going to be basing our model off of that. Our current baseline model is a cubic B-spline to interpolate values using the open source Splinter library. And we are planning on using the signal to noise ratio as well as log spectral distance as our loss metrics. Currently, we are building the B-spline code, and we have built the downsampling and bottleneck blocks, which the downsampling blocks involve a 1D convolution as well as using a ReLU. And then the upsampling blocks will also be 1D convolutions with dropout, ReLU as activation, as well as stacking from the downsampling blocks, so that you can use some of the data from the earlier blocks in the upsampling blocks. Thanks.